Well, my name is Isiah Kendall. I'm from Wright State University. I'm an undergrad studying biomedical engineering, and my research topic was the analysis of NFL concussions and the effects they have on the brain. There are many different sports that involve concussions, such as soccer, baseball, and basketball, but my topic of research was football because in this sport, concussions happen more commonly than the others. Just to give you a general process of how the concussion occurs, two objects are going to move towards each other. They're going to collide, the two objects representing the football players, and then their momentum is going to be transferred. And then lastly, the head is going to be affected by the collision, which can lead to a concussion. Here are some examples of the momentum being transferred in different situations. So the conservation of momentum states that the total momentum in any closed system will remain the same before and after the collision, even if the two objects are different weights or different speeds. So here I just list the conservation of momentum equation. So just to give an example of that, I have two football players colliding at different masses, 70 kilograms and 110 kilograms, and they're just going to collide and their momentums are going to be transferred. And here I show some numbers. The 6 represents the speed that they were going, and again the 70 and 110 were their weights. And here I show the momentum that each player obtained. So since the momentum in B was larger, it's going to transfer 240 kilograms per meter per second to A. And I simply got that by subtracting the 660 from the 420. So the walkway is, since there was 240 after the collision, then that means the total momentum before the collision was also 240. And there's a relationship between that, such that if you increase the mass or increase the velocity, you're going to proportionally increase the momentum. And likewise, if you decrease these, then you're going to decrease the momentum. So leading up to the concussion, I just want to give some background on some analysis and some stuff I looked into leading up to the concussion. So I'm going to go through the analysis of the helmet criteria and the neck criteria, and lastly the G-forces, which are going to be transferred to the brain, leading to the concussion. So I just looked at different widths and heights and lengths of the helmets, and I got the padding thickness, just trying to get some numbers together to find out some reasonable values of helmet designs. And likewise, I did the same thing with the skull. I got the thickness, the radius, and the overall weight that the player is going to have for his head. And just through my research, I found that the padding is actually going to work like an absorber and absorb some of that force. I'm going to talk a little more about that later. And here I just show a picture of the different types of pads in the helmet. And here I just show some formulas for calculating the stress and strain that the padding is going to feel when the force is collided into the helmet. More on this later as well, and this is just going to show how much pressure that the padding can take before it completely deflates. And now I'm going to talk about the neck injury criteria, likewise like the head. Again, I look at the width and height of the helmet because I was trying to find the center of gravity. Center of gravity is important when dealing with helmets because if the center of gravity is moved forward towards the head, put more pressure and stress on the neck, which can cause more problems to happen. So I just noticed that helmet D had some significant values. If the center of gravity is pushed more, so I just took that into consideration. And then I looked at the limits that the neck can rotate and which disc were responsible for that. So I just have those values there. And I also took into consideration the momentum equation, because that's how I was able to calculate how much force the neck was going to feel. So here I just show an example of what a football player may experience if they're going through a collision. I have a force coming in and extension happening at 55 degrees, which is reasonable, and it's between those limits from the previous slide I showed. Right here, so this should be okay as far as that. And just calculating the moment in this slide, and also showing the center of gravity was pushed forward, so that's going to put some strain on the neck as well. And I also found that with a longer face mask, a larger moment can happen, and that's just based on how the momentum equation works. If you increase the perpendicular distance, you're going to proportionally increase the momentum power. And just to give you a background of how much force the neck can actually take, it's around 4,000 newtons. And there's also a study done that the average football player is seeing around 66-31. So you're seeing that the neck is giving way, on an average basis. So to lower these values, they would just have to do more workouts with the neck. And lastly, I'm going to get into the transfer forces, and this will show how much G-force is actually that the brain is going to feel. Just to give you a background of G-forces, if you've ever rode a roller coaster and you've gone up a hill or something and you feel like your blood is rushing to your legs and you just feel more weight, you're experiencing an increase in G-forces. You have prolonged G-forces and you have temporary G-forces. Prolonged are more severe in lower numbers, and the temporary G-forces are more severe in the higher G-forces. And I just showed the different levels for the prolonged. You're going to gray out, black out, but you're still going to be conscious and have oxygen, and then G-lock is a worst case scenario. And just to give you an idea of what's bad as far as temporary G-forces, you can see that we experience G-forces on a regular basis, just as coughing and sneezing, but it's only when the G-forces are high, such past 100, which is what the NFL football players are going to experience, which leads to the concussions. So now I'm going to talk about the translational process, how much G-force is actually getting transferred to the brain, and how much the different materials are absorbing. So I found that if you take the Young's modulus equation and rearrange that for force, then you can actually calculate how much force that particular material is going to absorb as far as the concussion rate. So I just took the different materials. The helmet was made of the polycarbonate, so I calculated that, and likewise I did the same thing for the padding and the skull, and these are the values that I obtained. So the first scenario I took was how much force or G-force that the skull is going to absorb before it reaches the brain. So I just have a chart showing a scenario of that. I have an age group between 10 to 15-year-olds because I wanted to kill two birds with one stone. If young children are experiencing these kind of G-forces, then surely NFL players are as well, so it's a problem in both areas. The two columns to pay attention to are the weight and the reduced G-force. It's plausible that the 15-year-old can hit the 10-year-old because I took the 50 percentile mean of the body weight mean of the 15-year-old, and therefore took the 90 percentile body weight mean of the 10-year-old, and then likewise the 80% for the 11-year-old, and so on. And if you look at the reduced G-force column, you can see how much G-force the skull is actually reducing compared to the original G-force. And then below I just show the graph of weight versus G-force, reduced G-force. So similarly, I did the same thing for the helmet data with no padding inside. And the graph is going to look similar because there wasn't that much of a change, but you can see that the reduced G-force did go down further. And lastly, I did the same thing with the helmet with all the padding. And it turned out that the helmet reduced the G-force by roughly around 10 Gs, and that graph is shown. And then lastly, I show all the graphs together, and that's what that looks like. So in conclusion, current football helmets cannot prevent concussions entirely, but that's something that's an ongoing process. Research is being done to catch early symptoms of concussions. I read something where they're putting sensors inside the helmets so they can catch the impact that the player is feeling and therefore decide if they want to pull them out or keep them in. Further down the road, I want to continue my research and look at the designs of helmets and possibly create better helmets. And I just want to acknowledge my research advisor, Dr. Goswami, and OSGC for this opportunity. Thank you.